All right, so this is the last lecture here from Bloomberg Hall. Thanks for sticking with it. So next week there'll be no lectures, and if all goes well, I'll be in India the week following, and 6 more lectures in India. Okay, so it's been quite a marathon, but all right, but it's been fun going through all these topics. All right, so we talked about the Kondo lattice last time, and discovered quite a remarkable phase of matter in which the spins effectively became part of the Fermi surface, and you got a large Fermi surface, as it's called, whose volume counts not just the conduction electrons, but also the spins. This is sometimes called heavy Fermi liquid because the quasi-particles near the Fermi surface still remember a bit of the fact that they came from spins, and that makes them very heavy and have a very large effective mass. And so this is called a heavy Fermi liquid. And it's been a largely very successful theory of many intermetallic compounds, the so-called heavy fermion compounds, where you have typically a rare earth or transition metal that forms a spin, and then you have S and P electrons from other elements forming the conduction electrons. Okay, so today I want to come back to something we could have covered a long time ago. It's a basic relationship in Fermi liquid theory, which is the issue of the Fermi surface volume. So that's something that came up in the discussion of the Kondo lattice, where suddenly the spins appear to be mobile and part of the Fermi surface. And we'd like to understand how general is that phenomenon? Can you, when is it that some degrees of freedom are part of the Fermi surface, and when are they not? And for a long time, it was thought that, in fact, it's always the case. The phenomenon we discovered on the Kondo lattice is a very general phenomenon. And it goes by the name of the Luttinger relation, or sometimes called the Luttinger theorem. So I want to review that, and I'm going to review that in the context of just spinless fermions in a single band. There won't be multiple bands for now. We can extend it to multi-band case quite easily, and we'll get to that later. And the Luttinger relation, as the name goes, was, well, I don't know the precise history, but obviously Luttinger had an important role in it in the 60s. And it's a rather remarkable relationship, which tells you something to all orders or in the interaction, which I should emphasize not the same thing as exact, because it is really a perturbative relation, something that certainly in the older textbook is not well recognized. But it's something that's true to all orders of the interactions. Or more precisely stated, suppose you start with a theory with no interactions, and then you smoothly turn on interactions, and there's no phase transition, nothing remarkable happens as you turn on interactions. Then no matter how large the interactions are, there's a certain invariant. It's almost like a topological invariant, something that doesn't change. And what doesn't change is the volume enclosed by the Fermi surface.
So it is the exact same, as long as there's no phase transition.
Correct, yes. So I want to show you a version of the proof of this statement, which is rather similar to Luttinger's original arguments. It's been cleaned up a little bit. And in particular, the way I present it, what I'll emphasize, which is also not emphasized in the older textbooks, is the role of symmetry. So the Luttinger relation is really fundamentally connected to the conservation law of of the number of electrons, in this case, the density. And as long as there is this kind of U1 conservation law, then there is a Luttinger theorem. And this is, in fact, a much more general statement. It's also true for bosons. It's also, for any system which has a global U1 conservation law, in which the density, the charge density of that U1 charge can vary smoothly, you have to worry about the fate of this Luttinger relation. And where we're going with this is that we'll see there are phases of matter in which this Luttinger relation is not obeyed. So there's a modified relation that you have to worry about. There's still a statement of the consequence of the conservation of charge. But that requires, much more subtle arguments about exactly what that statement is. And there's still work on that these days. So, and in fact, there's connections, as we'll see, to various modern ideas on anomalies and so on. Okay. And spin liquid physics will also appear in there. But all of this is, of course, unknown to Luttinger and most physicists at that time. This was generally believed to be an exact statement for any metallic phase of electrons. But we'll see there are other phases of electrons, metallic phases, where it's not obeyed. All right, so we'll get to that eventually, maybe not today, but certainly by the next lecture. But let's just go back to the 60s and 70s and go through, cleaned up version of Luttinger's argument. Okay, so we just spinless electrons, which are mobile with some dispersion AK0, and you would just slowly turn on interactions while making sure you conserve number of particles. Also, you don't want to undergo a phase transition where you break this U1 symmetry, like in a superconductor. Then there is no Luttinger theorem. So once the symmetry is broken, this constraint can be pretty much forgotten. Okay, and that would be an important thing to consider as we go along. All right, so we have the electron Green's function, which if you remember from way back when, I'm mostly going to use the imaginary frequency Green's function at 0 temperature. So it's an exact statement that it's I omega minus EK0 minus some self energy, which will be a function of K and I omega. So you do perturbation theory, and to all orders, you can write the Green's function in this way. Okay, and way back in the very first chapter of the course, we talked about some exact properties of the self energy. And one important property was that the imaginary part of the self energy had all momentum. And as the frequency goes to 0, and this is at t equals 0, at t equals 0. So this is simply a statement that energy is conserved. And then if your particle wants to decay at very low frequency, it has no phase space to decay. You have a particle coming in with some frequency omega, and it's going to decay into 3 other particles. There's a 4-body interaction, something like this. And energy must be conserved, so this will have some energy, frequency omega 1, omega 2, omega 3. So you have to conserve energy in this process. So you get integrals of d omega 1, d omega 2, d omega 3, which have to be bounded by 0 because these are excitations, and there's an energy conservation law. So because these have to be positive, there just isn't enough phase space, essentially a version of Fermi's golden rule. And so you conclude, therefore, that the self energy must vanish as frequency goes to 0. Okay, there's probably, it is also a perturbative statement. There are phases of, even in actually non-Fermi liquids like the SYK model, as you can see, this is also true. So this argument is perturbative, but this is, I think, a much more general statement. Okay, so once this is true, then we notice something interesting here. So now we can define a Fermi surface. And here everything is a vector, although I won't put all the vectors everywhere. So the Fermi surface is defined at the point where, so it's at with some momenta, k equals kf. This is really, again, a vector, where ek0 plus the real part of sigma of kf, sorry, this is also kf, 0 equals 0. So the imaginary part vanishes as frequency goes to 0. And then there's a line in momentum space where the real part also vanishes. And that defines the Fermi surface. So there's some Fermi surface here where this is true. Okay, so that's the it's a all orders definition of the Fermi surface. You just do perturbation theory and work very hard, and you can get the Fermi surface. In fact, its shape will change due to interactions if you don't have full rotational symmetry. And these are things people can compute on the computer quite efficiently now. And you can measure this in perturbation experiments, so there's no question it's a real object. All right. And there are quasi-particle excitations near this Fermi surface, and their character changes from particle-like outside the Fermi surface to hole-like inside the Fermi surface. This was all something we discussed in the very first chapter. Okay, so now what we want to show is that the volume enclosed here, this volume, is it invariant, that it doesn't change. In fact, if you didn't have any interaction at all, you'll get some value. Now you turn on interactions, then the volume will remain the same, provided the total density remains the same. So what we want to evaluate then is the density of particles. So rho, which is the expectation value of C dagger K, CK. So from the Green's function, and now I have to get all the signs right. At least once check these signs very carefully. But okay, so this is going to be 1 over volume, sum on P. This is an equal time Green's function, but I have to be very careful about the convergence issues, I omega 0 plus. Okay, so the Green's function is defined as a time ordered Green's function, and we have to order the operators so that the dagger is to the left of the annihilation operator. And that accounts for the 0 plus. And I'm going in imaginary frequency here, d omega. Okay, so that's formally the exact statement. And what we'd like to do is to evaluate this. So the first thing you have to keep in mind is that this integral is very poorly defined. If you got rid of this thing, the integral is not defined at all because it's not convergent at high frequency. But once you put this very slight convergence factor, which orders the operators correctly, it's well defined. So g of omega, d of p, omega goes to infinity, always goes 1 over omega. So this thing is just marginally convergent, 1 over omega. There's a log divergence, but this thing gets rid of it at high frequency.
That was for omega goes to plus infinity. Maybe for minus infinity, it's okay by time.
No, it's true for either axis.
How can the EP of omega 0 plus help with both ends? Oh, sorry, it's oscillatory. So.
Yeah, okay. Yeah, it turns out to be okay. Right. Okay. All right, so we want to do this integral. So let's plug this in here. 1 over V, someone, I'm sorry, I've gone to P rather than K. Okay, let's go back to K. Let's plug this in here. And it's all about doing this integral over frequency, d omega over 2 pi, 1 over I omega minus EP, 0 minus sigma of K and I omega. Okay, and I omega 0 plus. All right, now, if this omega dependence wasn't here, then I could do this integral with just free particles, and there are other simpler ways of doing it, but you can also do it this way and work it out. So what we want to do is basically pull out the part that we can do. And the nice thing, it'll turn out that the part we pull out is in fact the dangerous part. It's the dangerous part that, where you have to worry about this convergence factor. So you pull that part out. And once you pull it out, the remainder, as you'll see, is much better behaved at large frequencies. And then you can prove lots of interesting things about it. So there's just a very simple identity which is behind all of this. And it's amazing how much digging it takes in the various textbooks to really see this is at the heart of it. Okay, so there's a very simple exact identity that I'm not going to write down. What I want to do is to write this object here as a derivative of something. Okay, so what is it the derivative of? All right, so even my own notes are not very clear, and display this identity in its full glory. Okay, minus sigma. I'm sorry, I'm mixing p's and k's all over the place because in my notes it's p's, or is k's. Okay, so first I'll say there's I d by d omega of the log of that, so let's just call that g of k and omega. So if I take the derivative of this, and if I got all my signs right, you will just get the term. So this, that is, if I take the derivative of this frequency inside the g, I will get what's on the left-hand side. So there's something left over, and what's left over, when you take this derivative of omega, this operates on the self-energy. So that's the new part that the interactions bring in. So we want to put that out. So the next part will be minus I g of p and I omega is d sigma k d sigma d omega of k and I omega. Okay. And now this is a very easy identity to identify, to check. You just take the derivative of this. When you take the derivative of the frequency, you'll get what's on the left-hand side. And when you take the derivative with respect to sigma, you'll get a term that cancels with this. All right, so now there's two parts to the Luttinger theorem. The first is to do the integral, frequency integral of this. Okay, that sounds like the world's easiest thing, but it's also a little subtle, but it can be done because it's the integral of a total derivative. Surely we can do that. And you could probably account for these convergence factors, you can work it out. And what that expression will give you is essentially the volume enclosed by the Fermi surface. So this part gives you exactly what you want. It has the same, I mean, it must really, if it's something simple, it must give the same value that when the self-energy was 0. And when the self-energy was 0, you know this is the volume enclosed by the Fermi surface. So if you can see that this doesn't depend much on the self-energy. And in fact, it doesn't, because the self-energy vanishes at high frequencies. And it's also a total derivative. So it's easy to see it doesn't depend on the self-energy. And so that's a quick way of saying that this is going to be the term you want. So then you're left over with something. Then the second part of the statement is that the frequency and momentum integral of this quantity vanishes. Okay, so those are the two things we have to establish. Let's do them in turn. Let's do the somewhat easier part, which is just evaluating the first term. So I'll take the first term there. And it's all about doing the frequency integral, d omega over 2 pi. So now I'm going to draw the complex frequency plane. And the integral is along the vertical axis here. So we're doing the integral along this axis. And that's because of the I omega and the argument of the Green's function. And remember, there's a branch cut. These are time ordered Green's function on this axis. And there's a branch cut here on the real axis. This goes right across the branch cut. You have to go back and remember all the Green's functions, the way we define them. And also the strength of the branch cut at very low frequency is very small because the self-energy vanishes at zero frequency. So in fact, it's, you know, there is a singularity at omega equals 0, but it's very weak. So we'll have to pay a little attention to that, but that's not so crucial. So but to evaluate this, what we're going to do is this is where the convergence factor comes in. So when I go on this side, then if I got the signs right, the convergence factor, it doesn't allow me to close the contour, but the convergence factor tells me I have to close it on this side. So I can close it on the other side. And so I'll evaluate this integral on this contour. And it's a total derivative. So in the end, you really have to look at what happens out here and out here. Now there's one confusing thing here. There's two ways there's a branch cut on the real axis. There's a branch cut in G, but there's also the branch cut in the log. And you have to consider them both very carefully. Okay, I have put a few steps in the, yeah, okay. Let's take a few steps here, but I'm going to have to refer to my notes. So we're going to call this direction Z, this frequency axis Z. And let's see. I mean, this is really the world's most complicated way to evaluate the density for free particles. Because you know it's got to be that the self-energy 0, that's the only answer that's there. Okay, so now you can write rho minus I over V, sum of K, minus infinity to 0, dz over 2 pi, d by dz, log of G of K and Z plus I0 plus, or log G of K and Z plus I0 minus. And these are the two parts of the contour, just above it, below the real axis. Okay. All right, so basically you have a contribution at minus infinity, and you have a contribution at 0. It turns out the one at minus infinity doesn't contribute. It's the same. This thing just goes to 1. But right at 0, there's a contribution that comes from the fact that the Green's function changes sign, and therefore the real part of the Green's function can change sign, and therefore the log can contribute a branch cut. Okay, so I'm just going to write down what this turns out to be and look at it carefully. This just turns out to be 1 over V, sum on K. When the real part of the Green's function changes sign, you get a contribution. And so it's theta of minus EP0 minus sigma of, K I0 plus. Okay. Which is in fact equal to the volume enclosed by Fermi surface. Simply from this definition right here. So when it's negative, you get a contribution to this integral, and that just gives you this volume.
Will be the real part of sigma or the sigma?
Again, the real part, the imagined part is 0 anyway, but you're right. That's just for emphasis. Yeah, it's 0 because of this. This is definitely non-zero. So this renormalizes the dispersion. So sometimes this is called just EK without the zero. And near the Fermi surface, it will be Fermi velocity times K minus KF. And the Fermi velocity is written as KF over n star. And this is the big mass. And so, well, it can become very big. So this can be really huge, the real part, but the imaginary part has to vanish. Yeah.
Can you say again why you have to close on the left and not?
Because of this convergence factor.
The convergence factor doesn't care if you're a negative real omega.
That's right, but no, it has to become, this becomes very small as you go out to infinity. And it has so that the integral converges on this side. There's also a big circle that you have to put in. And you have to argue that the contribution of the circle is zero.
Oh, where does the circle go? Can you? Oh, okay, I see.
Yeah. I can't guarantee the signs are right, but I did check them at once.
Yeah, it follows the arrows of the original contour.
You also have to go there.
Yeah, thank you.
So for this part to disappear, you can only close on this side. This all goes back to what you call a dagger and what is not, the normal ordering. Okay. All right, so we've got a contribution, which is very nice. And there's some hairy contour integrals, but really it's just a little bit of math. Once you know something about the analytic property of the Green's function, you can work this out. Of course, the easiest thing would have to be just evaluate the Fermi function, but anyway, this is at zero temperature also. Okay, where's my, oh, there, all right. So now we've got, put this back up. We've got this other contribution to worry about. Oops. Okay, a little bit of exercise there. All right, so we have this extra contribution, G d sigma d omega, and we now have to prove that that's zero, right? Or evaluate it. In fact, what happens in something like the S/K model, that contribution is not zero. But in the Fermi liquid, it is zero. So there's a second contribution you have to worry about, which may or may not vanish. All right, so we have to evaluate that object over there, which is G K omega, d sigma d omega, d omega k. And I don't have to worry about normalizations because at least pretty soon you're going to show that this is zero in general for all orders in perturbation theory. Okay, so that's the heart, that's the non-trivial part of the Luttinger theorem, proving that this contribution vanishes. Okay. All right, so there's a bit of formalism here that I'm going to have to rely on. But without proof, although there are proofs of it to all orders in perturbation theory, I want to now introduce what's in this context is called the Luttinger-Ward function.
I'm tempted to get the following argument. You showed that you got an answer that was universal. It only depended on the Fermi surface, not on the form sigma.
That's right.
So if you apply sigma of k omega by sigma of k0, you've gotten the same answer.
Yes.
So what else do you have to know?
Nothing else. Right. Yeah. So that, it's pretty clear that this answer, this is going to give you the simple answer. The non-trivial part is showing that the rest is zero. Yeah. So this is where symmetries and other things are going to come in. All right, so I'm going to introduce what's called the Luttinger-Ward functional. In these days where people are talking about G sigma theories, that's effectively what they're talking about. So what is the Luttinger-Ward functional? So it's a functional phi of the Green's function. So you give me a Green's function, an arbitrary function g of k and I omega. So you know this is a function of a function, hence a functional. The important part is the frequency here. So this is some function of frequency, and this is some function of that. So first of all, they exist a Luttinger-Ward functional, and then the self-energy is the variation of phi with respect to g. Okay. All right, so if there is such a functional whose variation with respect to g gives you the self-energy, then that's a very important ingredient in then proving that this thing vanishes to all orders and perturbations. So there is also the question of proving the existence of this functional. I'm not going to do that. Various books go through it in some detail. I have some references, but you can roughly see it kind of perturbatively anyway. You know, the first non-trivial term in this functional is a function of g. If you have, you know, something like this, you know, 4 g's, and when you take the variational derivative, that's like cutting one of these lines. So when you cut a line, you see you get a self-energy graph. You move this line, and you get a self-energy graph. That's this diagram here, something like that. Or you can cut this one, you cut this one, this one. So just by cutting lines on these functional graphs, you get graphs of the self-energy. Okay. And in various, you know, approximate theories, you can construct these functionals. Okay, so there exists such a functional, and then this functional has to have some interesting properties, some important properties, which is what I'm going to, which look kind of obvious when you first see them, but they are also intimately connected with symmetry. So there exists such a functional, and now I want to argue that also, if I shift the frequency inside the functional, that the functional doesn't change. So I take two different functions, phi of g of k and I omega, that the value of this functional is the same as the functional of g of k and I omega plus some small frequency, let's call it delta omega. So if I shift the frequency in this argument in all the Green's function by a small amount, the value of the functional won't change. Okay. So, you know, this seems kind of obvious again, just looking at this, all these frequencies are integrated over. So what difference does it make if I shift any one of the frequencies? That's just a variable of integration anyway. And so the value of the functional won't change. We do have to worry about convergence factors at infinity, but fortunately, all these graphs are well convergent. Everything that goes in the self-energy is well convergent. The only non-convergent pieces were these leading order pieces. Okay. You can also think of this in a different way. Suppose I did it, you know, the system itself has a symmetry, which is the rotation of C by some phase factor. Okay, I may not get the signs right here, but if you, there's a symmetry in the system, which is CK, goes to CK and some constant, theta is some phase. However, when I make the shift into G, so G of omega going to G of omega plus delta omega, that's the same as CK going to CK times e to the I delta omega tau up to a sign. So this is not quite a legal symmetry operation, but it's almost a symmetry operation because this angle theta is a linear function of time. The symmetry is for this when this is a constant. But you can go in and look at the original, certainly the interaction terms of the Hamiltonian, they're invariant under the symmetry. You can even make the symmetry time dependent because they're time independent local interactions. And they don't even have to be local in space. But as long as there is no retarded interaction, no time dependence in the interactions, this is still a symmetry of the interaction terms. It's not quite a symmetry of the free part, but we don't care about that really because we're looking at the contribution to the self-energy here. So, and this is roughly kind of an indication of the connection to modern anomalies, where we also take a global symmetry and you make it time or space dependent. So that's kind of what you're doing here. You're taking a global symmetry and making slightly local, at least in time, you're allowing for linear dependence in time. Okay. So now once you have this invariance, which again is relatively easy to show to all orders in perturbation theory. And here I'm just emphasizing this connection to symmetry, then we're almost done. So now I can take the derivative, expand this out to delta omega. So this implies when I take the linear term in delta omega, that I'm going to get d omega d phi on dg and dg d omega is equal to 0. That just follows from expanding this to linear order delta omega. Okay, well, this is really derivative, sorry. It's not a functional derivative. Okay, and what is d phi dg? That's sigma. Okay, and that's almost exactly what we wanted to prove, which is that this term g, d sigma d omega is 0. Okay, so then you have to integrate by parts. And you do also have to worry about various singularities right at this point and at infinity. So it turns out infinity is relatively easy because both sigma vanishes as 1 over omega, g vanishes 1 over omega, large omega, so there's no problems at infinity. At 0 here, there is a subtlety having to do with the fact that the nature of how the self-energy vanishes as omega goes to 0. So in a Fermi liquid, the sigma vanishes as omega squared. And that turns out to be fast enough that you don't have to worry about that contribution either. But as we'll see, and this was something Olivier Farquhar, Antoine Georges, and I discovered in 2000, there can be something dangerous even here where this doesn't vanish, and that happens in non-Fermi liquids like the SYK model. But anyway. All right, so apart from the subtleties, we have therefore established Luttinger's theory. Well, there's some homework to be done here, very carefully checked a lot of details, but they all work out. But this is a kind of an outline of the proof, and what I have particular want to emphasize is this connection to symmetry. So, for example, you could take free bosons and try to do the same set of manipulations. Take a Bose gas at 0 temperature with some interactions. Now we know that the interacting Bose gas is completely disconnected from the free Bose gas because there's Bose condensation at 0 temperature. But if you ignore that and try to do this, you would come up with a Luttinger theorem. But the actual state of the interacting Bose gas has a Bose condensate, so the symmetry is broken, and therefore you'll find that the resulting perturbation theory, which has both normal and anomalous Green's function, as we discovered in the Bogoliubov theory, where you have both Green's function of BB dagger, Green's function of BB. So because of that, you find that there is no such invariance in the Luttinger-Ward function. And that's because the symmetry has been broken. Okay, so that's why it's not needed for the Bose gas, because this symmetry disappears and there is no theorem. But as long as the symmetry is unbroken, and in principle, even a Bose system, you have to worry about this. So a simple example would be the following. Suppose I had a mixture of bosons and fermions. And then how can I stop the bosons from condensing? Well, what could happen is the bosons and fermions would form molecules. So there's more fermions than bosons, then some of the bosons will grab a fermion, form a molecule, and the molecule will be a fermion. So now you have a gas where the bosons won't condense, but it's made up of two types of fermions, a molecule and the bare fermion. And these objects now have to obey the Wright-Luttinger theorem. So they'll form two Fermi surfaces and be constraints on the Fermi surfaces. And they'll be constrained that the volume of the molecular Fermi surface must equal the number of bosons. And so on. So those are all can be derived by just variations of this argument. And the key there, of course, are the bosons didn't condense. So you do have to do, bosons have to do something rather drastic to stop the condensation. All right, any questions? Okay, so now we can go ahead and apply this to multi-band models. That's relatively simple. And then also think a little bit about what's going on in the Kondo lattice model. And that will open the way to things of matter where this is not obeyed, even though the symmetry is preserved. Yes.
You remarked that the Fermi surface could be measured experimentally.
Yes.
And when that has happened, does one really check this relation?
Oh, yeah, absolutely. So in the cube ray, it's been checked very accurately, and many other materials, absolutely. You can, especially in the last 20 years, with the precision of photo emission has increased tremendously. You can map out the details of the Fermi surface. You can also measure the Fermi surface by quantum oscillations, so oscillation and resistivity in the magnetic field. That probably in some cases gives even more precise measurements of the location of the Fermi surface. And typically you also have some estimate of the density of electrons. And so, yeah, it works, absolutely.
Why do you just a statement about the Fermi surface in momentum space?
Yeah, so
why do we need an estimate of the density of electrons?
Because that's what we have to check, right? The volume equal to the Fermi, so well, the Fermi surface must equal the density of electrons.
Oh, sorry. I was assuming that was known from the number of electrons per atom.
Yes, right. So if you have a stoichiometric compound, yes, but sometimes you have some dopants, and
you know their concentration, right?
Yes, yeah. So that's the hard part. Sometimes you don't know the concentration very precisely. Okay. Yeah.
Can I ask a question?
Yes, please.
Yeah. So related to this, like you mentioned, photo emission. So when you say volume of the Fermi surface, how strict of a definition of a volume that is? Like, can there be some sort of a non-trivial Fermi surface? For instance, I think I'll just take an example for cuprates about the arcs. So when you say volume, like in the Z direction.
Right, the arcs, yeah. So I'm going to come to the arcs. I don't think there's any such thing as arcs. I mean, if I take this definition of the Fermi surface, which is the zero of this function, that can't, the zero of this function has to be some sort of closed curve. And so at least this particular theory doesn't allow for this arc that ends into nothing. Unless there's some rather dramatic singularity in sigma at some point, okay, which there's no reason to expect that here.
Yeah, by arcs I just meant like a non simple case for a Fermi surface, right?
Right. So okay. So what this, since you mentioned photo emission, what this argument doesn't tell you anything about is the intensity of the photo emission peak. Okay, so to look at the full Green's function, there's a pole. So the Green's function right near the Fermi surface then has a pole, which is omega minus BF K minus KF. And the imaginary part is negligible. So there's a pole when K equals KF at zero frequency. but there's also a residue here. So in photo emission experiments, you're also sensitive to the value of Z. And it could well be that Z is a very small number. And that doesn't tell you anything about the integrity of the Fermi surface, which could still be perfectly well defined. What determines the integrity of the Fermi surface is the imaginary part of the self-energy down here, which determines the lifetime of the quasi-particles. And that could be very, very long, whereas this could be very small. That's in fact what happens in the heavy fermion compounds. So it could be when you're seeing an arc in experiment, you're not seeing the full enclosed curve because Z is very small on the backside of the arc. And for the cuprates, I think that's a very likely explanation. But we're going to come to this in great detail. This is a topic close to my heart. However, in the cuprates, that if you even assume that the arcs are closed curves, you run into a problem with the Luttinger theorem because the volume enclosed by those arcs or the closed arcs does not equal the density of electrons. So that's what we're going to come to shortly on when this theorem could be violated. But there can be, of course, multiple bands and multiple Fermi surfaces. They also come with a sign. What do you mean by enclosed? One side has electrons, the other side has holes. If it's the other way around, then the area counts as negative. So there's all these details that are simple extensions of these arguments. And once you add up all the electron and hole Fermi surfaces with the right sign, they could be multiply connected. Even this should be obeyed in any metallic system. That's what the Luttinger relation would say.
Thank you. And
the cuprates bring in a new level of complexity, which hasn't been seen before. But there are many materials with many complicated multiple Fermi surfaces. And with the right orientation, and if you work it all out, this should work. And it does work. It's remarkable how well it works.
The other quick question was about the applicability of the Luttinger theorem. So in the beginning of the class, we talked about how symmetry breaking phases and like it's hard. It's not applicable in a symmetry broken phase. But what about close to criticality? So on the top left of the board, when this term goes to zero, like for instance, if you are close to a critical point in the not symmetry broken phase, would fluctuations or can fluctuations play a part in the applicability?
So we'll come to that, and the answer is no. I mean, it's even holds at the critical point of various metallic critical points that have been studied. So what happens is that if you have a critical point, in a Fermi liquid, the self-energy as omega goes to zero, it goes as omega squared. And at various quantum critical points, you might find omega going to zero, going as omega to the 2/3 or something like that. And we'll see, in fact, see an example of that. In the SYK, that's a little different because in the momentum, it goes a square root of omega. And at least in both of these cases, in fact, the Luttinger arguments go through. You could get even breakdown of quasi-particles. You could have no quasi-particles. You could have complete breakdown of Fermi liquid theory. Nevertheless, the Fermi surface is sharp and the Luttinger theorem holds. So that's how general it is. What we're going to see shortly is to have a breakdown of the Luttinger theorem, you need topological order. You need something you need long range entanglement of the type that's present in spin liquids. Without that, you don't get a breakdown. So
thanks.
It's, sometimes I think Anderson used to say the tyranny of the Luttinger theorem. I don't call it a tyranny, we can get around it, but it's quite subtle. A quantum critical point is not sufficient.
I see.
Okay, we won't actually, this would be a good, maybe I can just show you how we get around it. I'll get to that shortly, but let me now just quickly apply this to the Kondo lattice, what we talked about last time. So we'll take the Anderson lattice model, which are two bands. So 1K, let's begin with that. Now I have to put the spins back in. And then I had some D level, epsilon B, B dagger, sigma, sigma. And then I had, actually I never wrote this down before, so maybe we'll write it down now. Minus W, somewhat I. I wrote on the Anderson impurity model. C dagger I sigma, D I sigma. And the only interaction term was U on each side and the I up, and the number of D electrons I down. All this UD. So the Anderson impurity model was, because the original model Anderson looked at, with this I was just zero, just some at the origin there was a large interaction UD. And then we showed that via canonical transformation, that was just the Kondo model. Neither Anderson nor Kondo, as far as I look at the lattice versions. But anyway, here it is. You just put the D orbital on every side. And then you can do a canonical transformation on the large UD, you'll get the Kondo lattice model. Okay, so what is the statement of Luttinger's theorem here? Well, it's relatively simple, except the Green's functions and everything we talked about become matrices. All right, so now the G is a matrix, GCC, GDD, GCD, GCD, and the total number of electrons, rho sub E, it's the usual integrals with a trace, because you just add up the number of C and the G electrons, and then you have the usual relation is d by d omega of trace G. This is trace log of G plus the trace of, again, keeping calculator of the signs of d sigma d omega. So really, it's very straightforward. You just put in traces everywhere, matrices, and the whole thing will just go through. The total density is equal to the volume enclosed by all the Fermi surfaces, and that's what you get from here. Because this will now have zeros, you can write this as log of the determinant of G, and the determinant of G is precisely where there are poles, and it could be multiple Fermi surfaces corresponding to zeros with the determinant. So it all goes through. Okay, the important point here is that it's only the total number of electrons that appears here. And the reason it's the total number of electrons is because the symmetry here is what's conserved, the U1 symmetry that's conserved, which you need for the Luttinger-Ward function of, is the symmetry that C goes to C e to the I theta, and D goes to D e to the I theta. There's only one global U1 symmetry because of this W term here. And therefore, there's only one Luttinger theorem, which is the volume enclosed by everything together. All right. Now okay, so that's true to all orders in UD. And you generally believe it holds forever, all the way up to UD equals infinity. And pretty soon, I'm going to give you an example of a system where it can't hold for very large UD. So we'll talk about that in a minute. All right. So in fact, there's only one Fermi surface, which could happen depending on the nature of W, as we saw last time. Then you would get a large Fermi surface will count all the electrons, including the C electrons and the D electrons. All right, now how about the Kondo lattice? Well, that's a little more subtle. It's not obvious how we prove Luttinger's theorem, because Luttinger's theorem doesn't work for spins, it's for electrons. It's not defined for spins. So the Kondo lattice is someone I, J Kondo, Si on every site on the spin of the conduction vectors. So how do I prove the Luttinger theorem for Kondo lattice? Yeah, well, we'll come to how you might do it, and there's a more subtle argument not involving the Luttinger approach, but I certainly can't do it using in any exact way using the methods of Luttinger, the traditional perturbation theory. All of this relied on, good old-fashioned G sigma theory. There's no obvious mixed theorem even or self-energy that's clearly defined for the spin. Okay, so you could just give up, or you can do what we did last time, which is the large M expansion. So in the large M expansion, we did express the partition function of this theory using this auxiliary field C and some F electrons. Okay, so we had some partition function, which is P squared. Again, I'll be schematic. And then you have P C dagger F, this complex conjugate. And then you had, well, of course, the dispersion K, and then you had lambda F dagger F. And you also had a d lambda. Okay. All right, so this theory, has a lot of symmetries, and we're going to come to that a little more carefully very shortly. But for now, let's just remember what we did last time. We didn't talk about the full theory. We just talked about a certain saddle point. So we looked at the saddle point where P was equal to P bar was not 0. And now all I want you to notice that the structure of this theory here at the saddle point is almost identical to the theory of the original Anderson model. This P bar, of course, has to be determined self-consistently. It's just replaced just like W. So at the saddle point, it's as if, as we emphasized last time, the F electrons, the F spin-ons have become electrons. They in fact mix. And the saddle point, there's only one global U1 symmetry in the saddle point once P bar is condensed. So once this is 0, the only symmetry is C goes to the e to the I theta, F goes to F e to the I theta. But it's important that it be this saddle point. And this is, of course, pointing the way to something more exotic that we're going to get to in a minute. But so from this structure, you can now see that to all orders, this implies that the Luttinger holds about the saddle point to all orders in 1 over M. So once I take the saddle point, then I can just turn the crank with the usual machinery, and then I have some, the usual time-ordered perturbation theory. I have lots of fields, but there's only one symmetry, and everything I said will just go right through the Luttinger-Ward functional works. And indeed, you would then conclude, yeah, that's great. Even the Kondo lattice, just like the Anderson models, obeys Luttinger theorem, and end of story. Okay. So, this is one of many failed attempts to try to get around Luttinger's theorem. Quantum critical point doesn't work. You go into infinity doesn't work. So pretty soon we can just throw up your hands and say, well, it just doesn't work. It always works. That's right. Luttinger's theorem always holds, and there's no way to get a metallic phase where you don't have the full large from the surface.
Well,
yeah.
The story with the spins, you found a Luttinger theorem, but it wasn't the traditional one.
But it is the same one as in the Anderson model.
That's true.
Right. So that was, I think that's what was the conventional feeling, was that in the Anderson model, it's obviously true. You derive this model from the Anderson model, the limit of large UD. And then you examine this theory as UD is practically infinite, a small jk. And then you find the saddle point, and you still find the same state. Okay. But of course, the key here is that this is entirely dependent on the saddle point. There could be other saddle points. And then you could violate Luttinger's theorem. And that is in fact the answer, how you get around it. But there'd be some other saddle point of this theory that does not obey Luttinger's theorem. Okay. So the answer is yes, and it's very easy to construct once you start thinking in this language. So the way to see it actually is not to take exactly the Kondo lattice model. This is sometimes called the Kondo-Heisenberg model, but it's in the spirit of the Kondo lattice model. This model is easier to see that such things can happen. So you have a Kondo coupling between on each side between the conduction electrons, C sigma 2 C dotted into S I plus the Heisenberg coupling on some lattice. Need not be nearest neighbors, but let me write it that way. Si dot H. Now, in fact, these couplings, sometimes they're called RKKY couplings in this context, are present in the original Anderson model. You start from the top model and do a 1 over UD expansion. I told you that you generated an exchange coupling between the local spins and the conduction electrons, which you will also generate couplings between the spins themselves. So this is called the RKKY mechanism from the Anderson model. So they're also there, and generally, they weren't ignored, but people have worried about them quite a lot. All right. So this is just another version of the model, in the same class of the original Anderson model, the two bands. Okay. So let's consider the case. Let's start with JK equals 0. Suppose you had JK equals 0. And let's say these spins are, since we just want to have an existence proof. So I'll give you an existence proof of the violation of Luttinger's theorem of this model derived from the original Anderson model, but you thought always hold. We put the spins, let's say, on a Kagame lattice. Some nicely frustrated lattice where you get a gap spin liquid state. Okay. So this is the spins are sitting here. And they form a spin liquid of some type. And if you want to be really rigorous, you could even say it has a gap. So this is, let's say this forms a spin liquid. In fact, you don't even need the gap order. Maybe with a gap. So what we have done by forming this spin liquid is, we've gotten rid of this tremendous degeneracy, which is what was leading to the to the large Fermi surface. The spins on their own have two states on each side, and they have no bare Hamiltonian. So there's a two-fold degeneracy on every side, or 2 to the n fold degenerate states, and the conduction electrons just don't like that, and so they effectively converted the spin to fermions. But suppose the spins on their own got rid of the degeneracy, and they form some state with fractionalization and emergent gauge fields, which we spent so much time talking about. Okay, so they've done that. And now there's a 4-fold degeneracy in a torus, but that's very small, very minor compared to the original degeneracy. It's only a global thing, but locally there's no degeneracy. And there's some spectrum of spin excitations. Okay. So the spins do this. And what do the conduction electrons do? Because they're not even coupled to the spins, which are formed as spin liquid. And the conduction electrons see from a Fermi surface, and this Fermi surface is small. Okay. So now this Fermi surface doesn't involve the spins because the spins are just living in a different world. They are JK equals 0. Okay. So this at least is a state that does not obey the same Luttinger theorem as the original Anderson law. Okay, and now the point is that the small Fermi surface size is stable. It won't change by the kind of arguments you presented to all orders in JK. In other words, I have this small Fermi surface which has got its G in and sigma, and then I just, all I need is a sigma that has certain properties. I don't, I can compute it in principle in perturbation theory in JK. And to compute sigma, all I need are the correlation functions of the spin liquid that have, all possible correlation functions of the spin liquid, which in principle can be determined. They could even be exponentially decaying because there's a gap. And so in all about on perturbation theory, it's hard, but knowing all the correlation functions of spins, I can compute the self-energy of the electrons. There's no infrared divergences or anything. And the reason there's no infrared divergences is because I've completely lifted the 2 to the n fold degeneracy of the spins by forming a spin liquid. And therefore, I can turn up JK to some large value. Now I have a coupled system, and it's formed a metallic state, but I have a small Fermi surface. So then I can, sometimes we call this state, this metallic state, sent to, with this name, called a fractionalized Fermi liquid. This was meant to be a play in words because Fermi liquid means no fractionalization. Well, this really has two sides to it, as both fractionalization and a Fermi liquid. Sometimes we call it FL star. And it obeys, okay, that's a bit too cheeky, a Luttinger star relation. The star meaning you don't count the spins, you just count the electrons. And this is a perfectly stable metallic state. It must be separated by a phase transition from U2 equals 0. And why must it be separated? Well, of course, one is that the Luttinger relation is different. The other is that there's a topological order here. There's some emergent gauge fields that have to be present. There are fractionalized excitations. And these are things you absolutely know nothing about in the original perturbations of the Anderson model. So the key to violating, if you want, one slogan, the key to violating the Luttinger relation is fractionalization and emergent gauge fields. Once you have that, at some point I would have said topological order, but I won't say that because that is too much potential for confusion with topological insulators, which do not have fractionalization. So key is fractionalization and emergent gauge fields, and that allows you to get around the Luttinger theorem.
Is it possible that the spins form singlets, but without giving rise to the gauge field?
No. Yes. So well, what state are you talking about? I mean,
well, I think you discussed previously some states where you adjusted the coupling so that you form just singlets in some.
Okay, so what happens there? You form a valence bond solid, for example, a crystal. Well, so what happens there, however, that's a very important point. You double the unit cell. Okay, so if you form a valence bond solid, say you did this on a square lattice, you could also do it on Calumet, but let's imagine you do it on the square lattice. Okay. So you double the unit cell. And so now how many spins are there per unit cell? 2. Okay. Now one thing that reminds me of something I haven't mentioned. The Luttinger theorem for spin-full electrons is always modulo 2, because you can always have a filled band. So, if you look at in this 2-band case, suppose the D band is fully filled, that would give you another contribution to the trace log G, but because it's fully filled, there won't be any contribution to the coming from the Fermi surface, it just comes from the fully filled band. I should have talked about that, but if I do this integral over the log and the band is fully filled, I just get 1 per spin. Okay. So what happens is, yes, you could get this state where the spins form a valence bond solid and the conduction electrons form a Fermi surface. But this state obeys the regular Luttinger theorem because all I'm removing from the difference between the small and the large Fermi surface is 2 electrons, not 1. You're always allowed to remove 2 for a spin-full system, or a spinless system 1. So Luttinger theorem is modulo integers per spin. And so once you double the unit cell and you don't have any emergent gauge field, this small Fermi surface state is perfectly stable, but it's not an exotic state. It obeys the conventional Luttinger theorem for that state.
If the spins were to form, let's say, ferromagnet, they all line the same way. Is that...
Yeah, well, ferromagnet, then again, there's no problem because then there's your broken spin rotation symmetry. So there's only, there are 2 separate Luttinger theorem for spin up and spin down. And for spin up, you're taking away 1, spin down, you're taking away 0, and that's also all right. And you'll get 2 separate Fermi surfaces, spin up and spin down. Yeah. Okay, so there is, but this opens up, this is a claim I'm making. And now I was too minded that I should do the more sophisticated argument. I think I will, but not today. There's a more sophisticated arguments, modern argument for the Luttinger relation, which make the connection between topological order and emergent gauge fields in a spin liquid with the Luttinger theorem for the Fermi surface. They're in fact both aspects of the same anomaly, having to do with what happens when you take the global symmetry of some type and you gauge it slightly, and then you ask for the action of that slightly gauged symmetry on different systems.
Is there a correction term? Is there a correction term to the Luttinger theorem in the case where there are emergent gauge fields? Can you characterize it using the emergent gauge field? Can you?
Yes. So that's what I'll talk about. So there is a Luttinger star relation, and the size of this Fermi surface is intimately connected to an appropriate anomaly of the spin liquid itself. Yeah. Now there's another term that comes, right? There's I think a nice paper by Bondison et al., which is probably the place that explained in a fairly sophisticated language. I'll present a simpler version of the argument for a specific case. Yeah, so we're going to come to all of that. This is kind of related to my statement at the beginning of this lecture that the Luttinger theorem, although discovered in the 60s and 70s, really is a 21st century theorem. It can be understood at a much more sophisticated level, and it's closely connected to many things in theories of gauge fields. Yeah.
A slight variation of the question. So
Yes.
let's say, for instance, it's not a valence bond solid. Like if you cannot double the unit cell, is the regular Luttinger theorem valid then? Let's say it's some disordered singlet state, which is not necessarily where you cannot extend the unit cell to.
Yeah. Hard for me to see how. Yeah, if you had a spin liquid with an emergent gauge field, it depends on what kind of spin liquid, but this is where it comes in. But for certain types of spin liquids, you can, like if this was a Z2 spin liquid of all the spins, then this Fermi surface has to be exactly this size of the conduction electrons, can't move from it. So there's a certain contribution to the full argument, which I can get by this approach from the spins, which is fixed once you specify the nature of the spin liquid. Yeah. So, I think the firm statement I can make is if the convention of Luttinger theorem is not obeyed, then there must be some emergent gauge fields. Exactly how much the electric fields, gauge fields take away will depend a bit more on the specific nature of the spin liquid you're talking about. But the simplest case is the one I've shown you here, where you just decouple the system and then couple them together. And then it's clear that this is completely stable. It's not going to change any order perturbation theory by just a simple extension of the arguments I presented today.
Thanks. Yeah.
Okay. All right, I just have a few minutes left. So let me just get started on doing a large M theory. So this is kind of a formal argument independent of any large M expansion. So what we can do now, and exactly as we did last time, just do a large M theory of this Kondo-Heisenberg model. This is really the direct sum of things you've done in great length in previous parts in the course. We apply the part-on construction to the spin liquid side, and then we apply the Kondo model analysis to the Kondo coupling. So just put the two together, and you will get a large M expansion, hopefully you can see it without too much formalism what's going to happen. So we take our spins and write them as in terms of the spin-ons. And now it's good that I'm calling them spin-ons because these will actually become spin-ons. There will be actual spin-ons in this FL star phase where we violate the theorem. Those spin-on excitations have to be present. Okay. So I make this decomposition and then I generalize to large M. So the sum 1K, some dispersion, I get K alpha, and this alpha which goes from 1 to M. And this is like JK over M, I alpha squared. And this one we've also seen before, is minus JH over M. Sum on nearest neighbors, S dagger I alpha, FK alpha, 1 squared. And then this term we met in the Kondo model, this term we met when we talked about spin liquids, and we just decouple them in the usual way, and we get a theory with let me set this up and then we'll come back to it in 2 weeks. And we'll talk about this. Yeah, maybe I just want to draw a table. Then we'll be all set. So let me be again rather schematic. So you decouple this term and you decouple this term. And so you'll get some terms like P squared, mod P squared plus mod Q squared that we met as spin liquids. T times C dagger F. And then you'll have Q times F dagger F. Okay. All right, so this particular theory has a global U1 symmetry. Which is C goes to C times e to the I theta. That's the conduction electrons. They're conserved in every term in the original Hamiltonian. And this also has a gauge U1, which we met on the spin liquid side, which is F goes to F times e to the I theta. Let me call this phi. Now it's space dependent. And Qij, we went to qij e to the I phi I minus phi j. But now this P also has this gate charge minus I phi. So there's a global U1 symmetry and there's a gauge U1 symmetry.
Under the global symmetry, either P or F must be charged.
Sorry, thank you. Yes. Yeah, so P has charges under both. Yeah, so let me just make a table. But this Qij, well, we met this before, that becomes a gauge field. So we're not so worried about the gauge field now. So this just becomes an emergent gauge field, which will couple to the other degrees of freedom, which we have to now worry about. So there's matter fields, there's three matter fields. There's the C, there's the F, which are fermions, and there's P. So we have a bosonic matter field here. And we have to worry about what happens to these gauge symmetries in various phases. Okay. Just by studying these symmetries, global and gauge, carefully, and thinking of the Kondo phenomenon as a Higgs mechanism, you can really understand everything. So therefore, I want to make this table here. The global U1, F, and the C, and the P. And okay, the signs, hopefully this is not charged in global U1, this is 1, and this is -1. And I have U1 gauge. This is charge 1, 0, and 1. And I can also define a linear combination of this from U1 diag, 1, 1, and 0. Okay. All right, so now the point is that, well, this is not an independent U1 gauge symmetry, it's just the difference of the sum of these two. The Luttinger arguments, in principle, apply even to the gauge symmetry. In fact, it's even better. Everything should work. So there are now really two Luttinger theorems. There's U1 and U1 gauge. And I have to ask, what is the fate of those Luttinger theorems? For every U1 symmetry, I have to ask, what is the Luttinger constraint? All right. Okay, so when the phase we've talked about before, the FL phase, the FL phase is characterized by P bar not equal to 0. So this tells me that U1 gauge is Higgs. So once that happens, there's no Luttinger theorem, no Luttinger constraint that I need to worry about for U1 gauge. However, and this you might think, well, this U1 is also Higgs, so okay, maybe, but U1 diag is not Higgs. So U1 diag is unbroken. Because P has 0 charge in a U1 diag. So there is a Luttinger constraint for U1 diag. And what does it count? Well, it counts both F and C. Okay. There is a Luttinger constraint. And that tells me the Fermi surface counts both F and C. Of course, that's the large Fermi surface. Okay, so that's just another way of understanding in a more modern language the fact that you have a large Fermi surface in the Kondo lattice. The unbroken symmetry in the Kondo phase, or the large Fermi surface phase, counts both F and the C as having a charge, and therefore there's a constraint which says that the whole Fermi surface must be large. Okay, and then of course the FL star phase, you can see it's very different. FL star phase that we're going to talk about is the phase where P is 0, at least the saddle point value of P is 0. So now I have two separate Luttinger theorems. P is a boson, so it doesn't form a Fermi surface or anything, it could in some exotic plan. So then if I apply the Luttinger theorem for U1, I would just say that the volume enclosed by the C Fermi surface must be the density of C electrons. That's it, because F is neutral. And then I'll get a separate Luttinger theorem, which is U1 gauge theorem, which is a theorem on the nature of the spin liquid. So this is where the nature of the spin liquid will come in. And so there are aspects of the Luttinger theorem in the spin liquid. Even in the Z2 spin liquid, we met it. We have all these constraints that you could not find a trivial state of bosons at half filling, and they have to be fractionalization, and you had exactly half filling. And there are all these emergent gauge excitations, Simons gauge theories, and so on. Those are all have some remnants or some version of the Luttinger constraint that applies from here. Okay. But I'll make that a bit more explicit, at least in a simple case next time. So that's the FL star phase where you have two Luttinger theorems. Both from U1 and U1 gauge. Okay. And they can lead to all kinds of exotic states. I'm sure the library of them has not been exhausted. And one of them is a simple example I showed you, but these were just approximately followed. All right. Okay, then. So any questions? All right, then. So I'll see some of you in India in a couple of weeks.